Imagine standing outside on a completely still night. No wind, no clouds moving across the moon, no sound except the quiet air around you. It feels like Earth is resting. The ground feels fixed under your feet. The stars look pinned in place, and the Milky Way, if the sky is dark enough to see it, seems like a pale, silent river stretched above the world. But that stillness is an illusion. Right now, while you sit or lie down and listen, Earth is spinning. It is racing around the sun. The sun is carrying every planet, every moon, every asteroid, every spacecraft, and every human being around the center of the Milky Way. And the Milky Way itself is not standing still either. Our entire galaxy is moving through space at an enormous speed, not drifting gently, not floating randomly. It is being carried through the universe by gravity on a scale so large that ordinary distance stops being useful. Galaxies, clusters, superclusters, dark matter, empty regions, and hidden walls of mass are all shaping its path. The strange part is that we cannot feel any of it. There is no vibration in the ground, no wind against the galaxy, no warning in the sky. And yet, the Milky Way is moving. The question is not only where, the deeper question is why. What invisible force is pulling an entire galaxy through space? Before we begin, if you enjoy calm journeys through space, subscribe to the channel, leave a like, and write in the comments where you are watching from and what time it is for you right now. It is always strange to remember that people can be watching the same universe from different places on Earth, under different skies, at different hours of the night. Tonight, you are watching the Just About Space channel, talking about the invisible force pulling the Milky Way through space. And to understand that force, we have to begin with a simple correction. The Milky Way is not moving through space the way a car moves down a road. There is no fixed cosmic road beneath it. There is no universal floor. There is no absolute background grid with arrows painted on it. In space, motion is always measured against something else. Earth moves compared with the sun. The sun moves compared with nearby stars. The Milky Way moves compared with other galaxies. And on the largest scale we can measure, we compare motion against the oldest light in the universe, the cosmic microwave background, the faint afterglow left from the early universe. That ancient glow comes from every direction. It is almost perfectly even, but not completely. One side of the sky looks very slightly warmer. The opposite side looks very slightly cooler. The difference is tiny, but it matters. It is one of the clearest signs that our region of space is moving compared with the early universe's background light. It is like hearing a soft cosmic wind without any air. The warmer direction is the direction we are moving toward. The cooler direction is the direction we are moving away from. Not because the light itself is pulling us, but because our motion changes how that ancient light reaches us. This is one of the first clues that the Milky Way is not just sitting inside the universe. It is traveling through it. But the path is not simple. The motion we measure is the result of many layers stacked on top of one another. Earth rotates once a day. Earth orbits the Sun once a year. The Sun orbits the center of the Milky Way over hundreds of millions of years. The Milky Way moves inside the local group, slowly approaching Andromeda. The local group moves through the larger cosmic neighborhood. And that neighborhood itself is being shaped by giant structures too large to fit inside any ordinary image of space. If you could pull back far enough, beyond Earth, beyond the solar system, beyond the local stars, the Milky Way would not look like a stationary island. It would look like one glowing system among many, all drifting within a vast gravitational current. The terrifying part is that this current is not visible as a single object. You cannot point a telescope at one star and say, "There is the force." You cannot look at one black hole and say, "That is what pulls us." The motion comes from imbalance. More matter in one direction, less matter in another. Clusters of galaxies gathered like heavy knots in the cosmic web. Voids, where there are fewer galaxies, leaving gravity weaker on one side. Dark matter halos that do not shine but still bend the paths of everything around them. The Milky Way is not being dragged by a rope. It is falling through an uneven universe. And falling, in astronomy, can be almost peaceful. A planet falls around a star, and we call it an orbit. A star falls around the center of a galaxy, and we call it a galactic year. A galaxy falls toward other galaxies, and we call it cosmic flow. The word sounds gentle, but the scale is not gentle at all. To make sense of this, imagine turning off the stars one layer at a time. First, remove the constellations. They are only nearby stars arranged by our viewpoint. Then, remove the planets. Then, remove the sun. Now, pull away from the Milky Way until its spiral arms shrink into a luminous disk. Around it, other galaxies appear. Andromeda, large and bluish. Triangulum, smaller but still vast. Dozens of dwarf galaxies, faint companions moving under the combined gravity of larger systems. This is the local group. It is not a cluster like the giant ones seen deep in space. It is more like a small family of galaxies, bound together in a quiet region between larger structures. Inside this group, the Milky Way and Andromeda dominate. They are moving toward one another. Not because they are engines. Not because space is pushing them together. Because gravity never stops adding up. Every star in Andromeda pulls on every star in the Milky Way. Every dark matter halo surrounds and strengthens that pull. Every dwarf galaxy adds a little more mass to the pattern. Over billions of years, those tiny pulls become a future merger. But even the local group is not isolated. It is moving too. That is where the real mystery begins. If the Milky Way and Andromeda were alone in an empty universe, their motion would be easier to understand. They would fall toward each other, orbit, merge, and eventually become one larger galaxy. But the universe around them is not empty. It is filled with a vast, uneven pattern of galaxies and dark matter. Some regions are crowded. Some are nearly empty. Some have long strings of galaxies, stretched like glowing threads. Some contain huge clusters with thousands of galaxies packed inside one shared gravitational field. The local group sits inside this landscape, and the landscape pulls. Astronomers notice this not by watching the Milky Way move directly across the sky, because that would take far too long, but by measuring the motions of other galaxies around us. When we look at distant galaxies, most of them appear to be moving away. This is not because they are all flying away from us through pre-existing space. It is because space itself is expanding, stretching the distance between galaxy groups over time. That expansion creates a general pattern. Farther galaxies tend to recede faster. This is the Hubble flow. But real galaxies do not follow that pattern perfectly. Some move a little faster than expected. Some move a little slower. Some have extra motion in a particular direction. These extra motions are called peculiar velocities. The name sounds small, almost polite, but peculiar velocities are one of the strongest clues that the universe is not evenly spread at local scales. They show where gravity has disturbed the smooth expansion of space. If many galaxies in one region seem to be pulled in the same direction, something massive may be shaping their motion. If a galaxy cluster has members falling inward, its gravity is visible even before all its mass can be seen. If a whole region of space has a pattern of motion toward one hidden area, astronomers begin looking for the source. That is how the story of the Great Attractor began. For years, astronomers studied the motion of galaxies near the Milky Way and found that many were not simply expanding away with the universe. They had an extra motion in a similar direction. The Milky Way, Andromeda, and many neighboring galaxies seemed to be moving toward a region of the sky, near the constellations Norma and Triangulum Australe. The name given to that hidden gravitational region was dramatic, but understandable. The Great Attractor. It sounds like a single monster in space. A cosmic magnet, a dark engine pulling galaxies toward it. But that name can be misleading. The Great Attractor is not a black hole sitting in the distance. It is not a single object with a surface or an edge. It is a region of unusually high mass, associated with clusters and superclusters, where gravity from many galaxies and dark matter concentrations combines into a larger pull. One of the important structures in that region is the Norma cluster, also known as Abell 3627. It lies far beyond the Milky Way, in a direction that is extremely difficult for us to study. And the reason is almost ironic. Our own galaxy gets in the way. When we look out of the Milky Way, we do not look from above the disk, we look from inside it. The galaxy surrounds us like a flattened city of stars. In some directions, we can see out through relatively clear windows. In other directions, the view is crowded with stars, gas, and dark dust. The Great Attractor lies close to the plane of the Milky Way in the sky. That means its light has to pass through the dense foreground of our own galaxy before it reaches us. Stars in the Milky Way outshine faint background galaxies. Dust blocks visible light. Gas adds confusion. The region becomes part of what astronomers call the zone of avoidance, a band of sky where the Milky Way makes it difficult to see the universe behind it. That name sounds almost like science fiction, zone of avoidance. But it is a practical problem. It is not that nothing exists there. It is that our own galaxy hides what is there. Imagine trying to study a city beyond a forest while standing inside the forest at night. You may see a few distant lights between the trees. You may detect smoke, movement, and reflections, but the full shape of the city remains hidden. For the Great Attractor, the forest is the Milky Way itself. This is why the story is so unsettling. The force pulling our galaxy through space comes partly from a region we had trouble seeing clearly for a long time. It was not hidden because it was magical. It was hidden because our viewpoint is trapped inside the system being moved. Astronomers had to use different wavelengths to uncover it. Visible light could not easily pierce the dust. Infrared observations helped reveal galaxies behind the Milky Way's plane, because infrared light can pass through dust better than visible light. Radio observations could detect neutral hydrogen gas in galaxies hidden from optical telescopes. X-ray observations revealed hot gas in galaxy clusters, showing where enormous concentrations of mass were gathered. Slowly, the hidden landscape became less invisible. The Norma cluster emerged as a major concentration of galaxies. Other structures around it helped explain why the local universe had a flow in that direction. But the explanation did not become simpler. It became larger. Because once astronomers improved the maps, they found that the Great Attractor was not the final answer. It was part of a bigger pattern. The Milky Way is not being pulled by one isolated lump. The entire nearby universe is a network of gravitational basins, filaments, sheets, clusters, and voids. The Great Attractor is one important piece, but it sits within larger structures that also shape our motion. This is where our sense of scale starts to break down. A galaxy is already enormous. The Milky Way may contain hundreds of billions of stars. Its disk is roughly 100,000 light-years across. Light itself, the fastest thing in the universe, needs 100,000 years to cross it from one side to the other. But galaxies are only the building blocks. They gather into groups. Groups gather into clusters. Clusters gather along filaments. Filaments surround voids. And on scales of hundreds of millions of light-years, the universe looks less like scattered islands and more like a cosmic web. In that web, matter does not form a smooth fog. It collects along threads. Huge, empty regions expand between those threads. The Milky Way is inside one of these arrangements. and its motion is the result of this uneven structure. A good way to picture it is not a magnet, but a landscape. Imagine placing a marble on a surface that is not flat. There are slopes, valleys, hills, and basins. The marble rolls not because one point commands it, but because the entire landscape has shape. Gravity gives the universe that shape. Dense regions act like valleys. Low-density regions act differently, not by pushing in the ordinary sense, but by providing less gravity than surrounding regions. When everything around a void pulls less strongly from that side, the combined effect can help direct motion away from emptiness and toward mass. This is why the phrase invisible force is both accurate and dangerous. Accurate because gravity itself is invisible. Dangerous because it makes the force sound like a single thing. In reality, the Milky Way is responding to a map. The map is made of matter. Most of that matter is not even bright. The stars and galaxies we see are only part of the gravitational story. Dark matter, which does not emit light the way stars do, seems to form large halos around galaxies and clusters. It adds mass without adding ordinary brightness. It shapes orbits, bends light, holds clusters together, and helps build the cosmic web. When the Milky Way moves, it is not only responding to visible galaxies, it is responding to the full mass distribution around us. Stars, gas, dust, galaxies, galaxy clusters, dark matter, and perhaps most importantly, the difference between crowded regions and empty ones. This is why the motion of the Milky Way is not a simple arrow drawn through a blank page. It is a path through a living gravitational structure, not living in the biological sense, living in the sense that it evolves. Clusters grow, galaxies merge, empty regions widen. Filaments feed matter into denser nodes. The universe changes shape over billions of years. The Milky Way is carried along inside that change. To understand the motion more clearly, we need to separate several kinds of movement that are often mixed together. First, there is the motion of the Sun around the center of the Milky Way. Our solar system is located far from the galactic center, inside the disk, in a region between major spiral structures. It takes the Sun roughly a couple 100 million years to complete one orbit around the galaxy. Since Earth formed, the Sun has gone around the Milky Way many times, but not thousands of times. Galactic time is slow. Second, the Milky Way has motion within the local group. Andromeda and the Milky Way are approaching each other. In a few billion years, they're expected to interact and eventually merge. This does not mean individual stars will mostly collide. Galaxies are mostly empty space, but their gravitational fields will distort, stretch, and reshape both systems. Third, the local group has motion compared with the cosmic microwave background. That is the motion connected to the larger cosmic flow. This is the one that points us toward the invisible force. When scientists measure the CMB dipole and compare it with galaxy surveys, they try to identify how much of our motion can be explained by nearby mass concentrations. The challenge is that no one structure gives the whole answer. Virgo matters. The Great Attractor region matters. The Shapley concentration, a huge collection of galaxy clusters farther away, may matter. Voids matter too. The result is not one hand pulling us, but many gravitational influences adding together. This makes the Milky Way's motion more disturbing, not less. A single attractor would be easier to imagine. One destination, one source, one cosmic object. But the real universe is more like a dark ocean with currents crossing at many depths. Our galaxy is not sailing by choice. It is embedded in the current. And unlike an ocean current, this one is made from space-time and mass. When astronomers map these flows, they are not only asking where galaxies are, they are asking where galaxies are going. That is a different kind of map. A photograph of the universe shows positions. A flow map shows motion. It turns the cosmic web from a frozen structure into something dynamic. Galaxies are not randomly scattered beads. They stream, they fall, they gather. They avoid emptier regions. They trace the invisible architecture of gravity. One of the modern attempts to describe our cosmic neighborhood uses the idea of Laniakea, a vast supercluster-like region that includes the Milky Way and many other galaxies. The name means immense heaven in Hawaiian, and it refers to a basin of motion, a region where galaxies appear to flow toward a common gravitational direction. In this picture, the Milky Way is not just in the local group. It is part of a much larger flow. The galaxies around us can be thought of like drops in a watershed. On Earth, rain falling on one side of a mountain ridge flows into one river system, while rain on the other side flows somewhere else. In the cosmic version, galaxies move along gravitational flows instead of water channels. The boundaries are not mountain ridges, but regions where the direction of motion changes. Laniakea is one way to identify the gravitational basin that contains us. It helps make the invisible visible. But even here, there is a warning. Cosmic structures on these scales are not always bound forever. Cosmic expansion is still happening. Dark energy appears to be accelerating that expansion. Some structures that seem connected now may not remain connected in the far future. Some flows may never result in final collapse. Some names we give to the cosmic web are useful for mapping, but they do not always mean the same thing as a stable object. A galaxy is a bound system. A cluster can be bound. A supercluster may be more like a temporary pattern in the expanding universe. This is why the question of what pulls the Milky Way is complicated. The Milky Way is pulled by mass, yes, but the mass is distributed across a universe that is also expanding. It is pulled by nearby structures. It is influenced by farther concentrations. It is moving with the local group. It is approaching Andromeda. It is affected by hidden mass behind our own galaxy. It is part of a flow that may never end in the way the word destination suggests. There may be no final point where the Milky Way arrives and stops. Gravity does not work like arrival. It keeps changing the motion as long as mass exists nearby. The story becomes even more strange when we remember that the Milky Way itself is not rigid. When people say the Milky Way is moving, they often imagine the entire galaxy traveling as one solid object, like a glowing disk sliding through blackness. But a galaxy is not solid. It is a huge gravitational system made of stars, gas, dust, dark matter, magnetic fields, cosmic rays, and orbiting satellites. Different parts of it move in different ways. The disk rotates. The halo surrounds it. Globular clusters orbit in old looping paths. Dwarf galaxies fall in, stretch, and sometimes dissolve into streams. The Magellanic Clouds, two nearby dwarf galaxies visible from the southern sky, are interacting with the Milky Way and leaving trails of gas. The galactic center contains a supermassive black hole, but that black hole does not tow the entire galaxy through space like an engine. It is massive, but not massive enough compared with the whole galaxy to control its motion through the cosmic web alone. The Milky Way's movement through the universe is the motion of its shared center of mass. But inside that system, everything is also moving locally. It is like a city on a moving ship, where every person, car, machine, and elevator has its own motion, while the ship itself crosses the sea. Only the Milky Way is not a ship. It has no hull, no captain, no destination chosen by intelligence. It is a gravitational storm that looks calm because we live inside it. If you could somehow leave the galaxy and watch from a distance, the Milky Way would not appear to rush through space the way a meteor streaks through the atmosphere. There is no air to heat, No trail of flame, no shockwave in the ordinary sense. It would simply drift against the deeper background, its spiral disk rotating, its halo carrying ancient stars, its satellites following, while the whole system slowly changes position relative to the cosmic microwave background and nearby galaxies. The speed is enormous by human standards, but the distances are so much larger that the motion looks slow on cosmic screens. This is one of the hardest things about astronomy. Fast can still be slow. A spacecraft moving tens of thousands of kilometers per hour may take decades to cross the solar system. A star orbiting the galaxy at hundreds of kilometers per second may take hundreds of millions of years to complete. One loop, a galaxy moving through the cosmic web, may cover unbelievable distances, but the universe is so vast that the journey remains almost invisible across a human lifetime. We are not built to sense cosmic motion. Our bodies evolved for falling stones, running animals, rivers, storms, and days, not for galactic flows. The only reason we know the Milky Way is moving this way is because instruments extended our senses. Microwave detectors measured the afterglow of the early universe. Telescopes measured galaxy positions. Spectrographs measured redshifts. Surveys mapped hidden clusters. Computer models reconstructed gravitational flows. X-ray observatories revealed hot gas in clusters. Infrared and radio observations looked through the Milky Way's dusty plain. Every part of the story required a different kind of eye. And even then, the picture is incomplete. The zone of avoidance still makes the map harder. Dark matter still cannot be seen directly. Distances to galaxies carry uncertainties. Peculiar velocities are difficult to measure precisely. The farther out we go, the harder it becomes to separate local motion from cosmic expansion. This does not mean the story is weak. It means the universe is difficult. It means our galaxy's motion is not a fact discovered by one photograph, but a conclusion built from many independent clues. That is often how real astronomy works. The universe rarely hands us labels. It gives us light. Sometimes that light is blocked. Sometimes it is stretched. Sometimes it arrives as microwaves from the early cosmos. Sometimes it comes from galaxies hidden behind dust. Then we have to reconstruct the invisible. The Great Attractor is a perfect example. For a long time, the motion suggested something massive. But the obvious view did not show enough. The Milky Way's own disk blocked the background. Astronomers had to ask a strange question. What if one of the most important structures affecting our galaxy is hidden behind our galaxy? That idea sounds almost absurd, but it is true in a practical sense. The Milky Way is both our home and our obstacle. It gives us stars, planets, chemistry, and the environment that made life possible. But it also blocks part of the universe from our view. We see from inside a dusty spiral system, and that viewpoint has consequences. To map what pulls us, we must look through our own home. The more scientists studied the region, the more they found that the Great Attractor was not empty myth. The Norma cluster and surrounding mass concentrations were real. They could help explain part of the flow, but they did not end the mystery. Because beyond the Great Attractor lies another enormous region of mass, the Shapley concentration. This is one of the richest concentrations of galaxies in the nearby universe. It lies much farther away than the Great Attractor, but because it contains so much mass, it may contribute to the broader motion of our cosmic neighborhood. This changes the picture again. The Milky Way is not simply being pulled toward the nearest large overdensity. It may be responding to a chain of structures at different distances. Virgo, Hydra Centaurus, Norma, Shapley, other clusters and walls, and the dark matter connecting them. The invisible force becomes less like a single arrow and more like a sum of many arrows, each with its own strength and direction. If you have ever stood in a river where several currents meet, you know the feeling in a small way. One flow pulls from the side, another pushes around your legs. A deeper current moves differently from the surface. You remain in one place only if you fight all of them at once. The Milky Way does not fight. It follows the combined gravity, but unlike water, these currents do not need contact. They act across millions of light years. They are written into the shape of space-time itself. This is why the word invisible can feel inadequate. We are not being pulled by something hidden just behind a curtain. We are being shaped by a structure so large that the Milky Way is only one glowing point inside it. The galaxy is not the main character of the cosmic web. It is one participant. And humans are smaller still. A species on one planet, around one star, inside one galaxy. Moving with that galaxy through a gravitational landscape we only began to map recently. There is another reason this motion is unsettling. It means that the night sky is not a fixed backdrop. The stars look permanent because human lives are short. But nothing is truly fixed. Nearby stars move. Constellations distort over tens of thousands of years. The Sun orbits the galaxy. The Milky Way and Andromeda approach. Dwarf galaxies fall in and become streams. Clusters tug on groups. Voids grow. The cosmic web evolves. The still night is only a slow frame from a moving film. If you could speed up time enough, the universe would not look silent. It would flow. Galaxies would gather along filaments. Clusters would grow. Some galaxies would merge in slow, luminous collisions. Others would drift into isolation. The Milky Way would not remain the same spiral forever. And our larger motion through space would be part of that long transformation. To make the invisible force clearer, let us return to the ancient light. The cosmic microwave background was released when the universe became transparent, long before stars and galaxies existed. At that time, the universe was filled with hot plasma, and light could not travel freely for long, because it kept scattering off free electrons. As the universe expanded and cooled, electrons joined with nuclei to form neutral atoms. Light was then able to travel across space. That light has been stretched by the expansion of the universe into microwaves. Today, it surrounds us from every direction. It is not coming from one wall at the edge of space. It is the cooled radiation from the early universe arriving from the farthest visible regions in every direction. Because it is so uniform, it provides a useful cosmic reference frame. When one side of the CMB appears slightly warmer and the opposite side slightly cooler, that dipole tells us about our motion through that background. This measurement is powerful because it is not based only on nearby galaxies. It uses the early universe itself as a reference. But the CMB dipole gives us motion, not a complete cause. It tells us that we are moving compared with the cosmic background. Then scientists ask, what distribution of matter could have produced that motion? This is where galaxy surveys become essential. A survey maps galaxies across huge regions of space. The more complete the survey, the better the gravitational map. But the map is never perfect. Some galaxies are too faint. Some are hidden by dust. Some distances are hard to measure. Some mass is dark. And the universe is three-dimensional, while our sky is a two-dimensional view with distance added through measurement. Still, the pattern is visible. The local universe is not uniform. Matter is clumped. The Milky Way lives near the edge of structures, near voids, inside flows, among other galaxies whose motions tell us that gravity is guiding them. One of the strangest realizations is that emptiness can be part of the story. A void does not pull the way a cluster pulls. A void is not a material object. But because it contains less matter than average, there is less gravitational attraction from that direction. In the combined balance of forces, galaxies can appear to move away from underdense regions while falling toward overdense ones. This does not mean a void pushes like a hand. It means the gravitational field is unbalanced. If a dense region is in front and an empty region is behind, the result can look like attraction from one side and retreat from the other. Later, this idea will become important when we talk about the possibility that the Milky Way's motion is not only caused by what lies ahead, but also by what lies behind. A region of relative emptiness may help explain why our galaxy is moving the way it does. For now, the key point is this: the invisible force is not one mysterious beam. It is gravity from the cosmic web, and the cosmic web contains both matter and absence, both crowded regions and empty regions, both shining galaxies and unseen dark matter, both local structures and more distant concentrations. This makes the Milky Way's motion a kind of fossil record. It tells us about the matter around us. If the galaxy is moving in a certain way, something in the universe shaped that motion. Motion becomes evidence, not just of where we are going, but of what surrounds us. The problem is that the evidence is hard to read. Suppose you wake up on a boat in fog. You cannot see the shore. You cannot see the current. But by watching the boat drift, by measuring its speed, by tracking its direction, and by listening to distant waves, you can infer something about the water around you. Astronomers are doing something similar with the Milky Way. We wake up inside a moving galaxy. We cannot step outside the universe. We cannot place a marker in absolute space. But we can measure light. We can compare directions. We can map galaxies. We can detect the CMB dipole. We can infer the shape of the current. And the current tells us that we live in a universe where motion is never isolated. Every galaxy is part of a larger environment. Even a galaxy that looks alone has a history. It formed from matter that flowed along filaments. It may have swallowed smaller galaxies. It may be falling into a group or cluster. It may be shaped by voids around it. The Milky Way is no different. It feels like home because we live inside it. But cosmically, it is one moving structure among billions. The invisible force pulling it through space is the combined gravity of the universe near us. And that answer is both scientific and almost impossible to picture, because combined gravity has no face. The Great Attractor gave the mystery a name, but the name may have made it too simple. It made people imagine one target, a hidden monster, a place where the Milky Way is being dragged. The real story is wider, and in some ways more frightening. There are enormous concentrations of matter we can only partly see. There are voids whose emptiness affects motion. There are dark matter structures that weigh more than the visible stars. There are flows stretching across hundreds of millions of light years. There are limits to our view created by our own galaxy. And all of it adds together into the motion of the world we call home. No one on Earth can feel the pull of the Great Attractor when they stand outside. The force on a human body from distant galaxy clusters is unimaginably weak compared with Earth's gravity. You are held to the ground by Earth. Earth is held to the Sun. The Sun is held in the Milky Way. The Milky Way is guided by larger structures. Gravity works in layers. Each layer dominates at its own scale. This is why the invisible force does not tear us away from Earth. It does not create wind. It does not shake buildings. It does not bend trees. It acts on the galaxy as a whole over immense time. The effect is only obvious when the scale becomes large enough. A human life is too small. A planet is too local. Even a solar system is not enough. You need galaxies. You need clusters. You need the oldest light. Then, the motion appears. This is one of the quietest, terrifying facts in astronomy. The universe can move you without making a sound. The most powerful motions are not always dramatic at the human level. They can be silent, steady, and too large to notice. The Milky Way is being carried through space, and every night sky we see is part of that journey. The stars above us are not a ceiling, they are passengers. The sun is a passenger. Earth is a passenger. Every ocean, mountain, forest, city, and sleeping person is being transported by a galaxy whose path is shaped by things most people will never see. And this leads to a question that seems simple but is not. If the Milky Way is being pulled, will it ever reach the thing pulling it? The answer is complicated. For Andromeda, yes, in a sense, the Milky Way and Andromeda are expected to merge far in the future. That is a local gravitational relationship strong enough to overcome expansion between them. For the Great Attractor, the answer is less direct. The universe is expanding. The structures involved are not all bound in a simple way. The Great Attractor region is not a single destination with a surface. The Milky Way may never arrive there like a spacecraft arriving at Mars. And as maps improve, scientists have found that the Great Attractor is only one part of a larger velocity field. The Milky Way's path is not a straight line to a cosmic endpoint. It is a changing flow inside a changing universe. Even the phrase "pulling through space" can hide the reality. Space itself expands between large-scale structures. Gravity pulls matter together locally. The motion of galaxies is the result of both effects. In bound systems, gravity wins. Inside galaxy groups and clusters, galaxies can orbit and merge. Between distant unbound systems, expansion dominates. On intermediate scales, the balance is subtle. Our cosmic neighborhood is still close enough for gravity to create flows, but not every large structure we name is necessarily a future home. Some are patterns in the expansion. Some are temporary alignments in a web that stretches as the universe ages. This matters because it changes the emotional meaning of the Milky Way's motion. It is not necessarily a journey toward a final meeting. It may be a motion shaped by an enormous pattern that will never fully close. The galaxy is falling through a universe that is also pulling itself apart at the largest scales. That tension is part of the modern cosmic story. Gravity builds, expansion separates, matter gathers. Dark energy accelerates distance between far regions. The Milky Way lives in the middle of these competing facts. At small scales, the universe makes structures. At large scales, it removes them from one another. The invisible force pulling the Milky Way is therefore not only a story about attraction, it is a story about limits. There are places whose gravity affects us now. There are places whose light reaches us now. There are places whose future influence may fade as expansion continues. There are structures we can map but never visit. There are motions we can measure but never feel. The universe is not only vast, it is dynamic in ways that our instincts were never meant to understand. A person can point at the Milky Way in the night sky and think of it as a band of stars. But that band is a moving galaxy inside a moving group, inside a flowing supercluster-like region, inside a cosmic web that has been evolving since the early universe. The sky is not still. It only looks still because we are watching one instant. If you could mark the position of the Milky Way against the cosmic background and return millions of years later, the mark would not line up the same way. If you waited hundreds of millions of years, the sun would have moved far around the galaxy. If you waited billions of years, Andromeda would dominate the sky. If you waited longer, the local group's future would be shaped by merger, isolation, and the accelerating expansion of the universe. Our current motion is only one chapter, but it is a chapter that reveals the hidden architecture around us. One reason the topic is difficult is that words like direction and destination become slippery on cosmic scales. If you say the Milky Way is moving toward the Great Attractor, that sounds like a clean direction. But the universe does not provide a simple coordinate system that feels natural to humans. The direction is measured relative to frames, maps, and background radiation. The Great Attractor region itself is part of a larger flow. The Shapley concentration lies beyond it. The local group has internal motion. The Milky Way's disk is tilted relative to other coordinate systems. Our solar system moves around the galactic center, and from Earth, all of these motions are layered into one experience that feels like stillness. So the invisible force is not invisible only because we cannot see gravity. It is invisible because the motion is hidden under layers. You cannot look up and isolate it with your eyes. You cannot feel it in your body. You cannot watch the Milky Way shift in real time. You need abstraction. You need measurements. You need patience. You need to trust that a tiny temperature difference in ancient microwaves tells us something real about the motion of our cosmic home. That is a strange kind of knowledge. But it is also beautiful. The Milky Way's motion is not guessed from mythology. It is measured from light. The same universe that hides the Great Attractor behind dust also gives us the tools to infer it. The same cosmic background that began before galaxies existed helps us measure the motion of galaxies now. The same redshift that reveals expansion also reveals deviations from expansion. The same dust that blocks visible light can be partly bypassed by infrared and radio astronomy. Every obstacle becomes a new method. And every method adds another piece to the map. Still, the map remains incomplete enough to keep the mystery alive. How much of our motion is caused by the Great Attractor region? How much by Shapley? How much by Virgo and other nearby structures? How much by voids and underdense regions? How much by mass hidden behind the Milky Way? How much by dark matter we do not directly see? The answer depends on models, surveys, distances, and definitions. That does not make the motion unreal. It makes the cause distributed. It makes the invisible force less like a single secret and more like a whole hidden geography. A geography of gravity, a map of where matter has gathered since the early universe. To understand why the Milky Way moves, we have to understand how that geography formed. In the early universe, matter was not perfectly smooth. It had tiny variations in density. Some regions were slightly denser than others. Gravity amplified those differences over time. Denser regions pulled in more matter. Less dense regions became emptier. Over billions of years, small differences grew into galaxies, clusters, filaments, walls, and voids. The cosmic web is the mature form of those early seeds. The Milky Way exists because matter was uneven. The Great Attractor exists because matter was uneven. Voids exist because matter was uneven. Our motion exists because matter was uneven. If the early universe had been perfectly smooth, there would be no galaxies, no stars, no planets, no people asking why the galaxy moves. So the same imperfections that made us possible also pull us through space. That is one of the deepest connections in this story. The invisible force is not separate from our origin. It is part of the same gravitational history that built the Milky Way itself. Gravity gathered the gas that formed the first stars. Gravity built galaxies. Gravity assembled clusters. Gravity shaped the cosmic web. Gravity now guides the motion of the galaxy that contains us. We are not being pulled through a universe that is unrelated to us. We are being carried by the same structure that produced our home. That makes the motion less random, but not less frightening. Because it means the universe is not arranged for stillness. It is arranged for change. Matter falls. Systems merge. Structures grow. Voids expand. Galaxies move. And we live inside that motion without ever noticing it. In ordinary life, a child looking at the night sky sees stars. An astronomer looking at the same sky sees velocities. Approaching galaxies, receding galaxies, rotating disks, orbiting stars, moving clusters, ancient radiation shifted by our motion. The sky becomes a record of movement. Not everything in that record points the same way. That is why models matter. A model lets scientists test whether a certain distribution of galaxies can explain the measured motion. If the known matter produces too little pull, there may be missing mass, hidden structures, or contributions from farther regions. If the direction does not line up, the map may be incomplete. If different surveys disagree, uncertainties have to be reduced. This is slow work. It does not look as dramatic as a rocket launch. No flame, no countdown, no explosion. But it is how humans discovered that our galaxy is part of a cosmic flow, one measured galaxy at a time, one hidden cluster at a time, one correction to the map after another. The Great Attractor was not found by someone seeing a giant object in a telescope and naming it. It was inferred from motion, then gradually associated with real mass concentrations as observations improved. That is important. Sometimes in astronomy, motion tells us about what cannot yet be seen. Neptune was predicted from the motion of Uranus before it was observed. Dark matter is inferred from gravitational effects on galaxies and clusters. Black holes are revealed by stars and gas moving around them. The Great Attractor was approached through the same logic at a larger scale. Something was affecting motions. So, astronomers looked for the mass. The universe often announces invisible things by moving visible things. The Milky Way's motion is one of those announcements. And it is still speaking. The more completely we map the nearby universe, the more detailed the message becomes. One day, surveys may fill in more of the zone of avoidance. New infrared data may reveal galaxies currently hidden. Radio surveys may trace gas through the dust. X-ray observations may map hot cluster gas more clearly. Gravitational lensing may help trace dark matter. Better distance measurements may refine peculiar velocities. Then, the invisible force will become less mysterious, but not less immense. We may learn that the Great Attractor is not the main actor people once imagined. We may learn that Shapley matters more. We may learn that voids play a larger role. We may learn that the local group's future path is different from older maps. Science often replaces a simple mystery with a more accurate, more complex one. That is not a failure. It is the process. There is another practical reason the mystery stays alive. Distance in the nearby universe is hard to measure with the precision we want. A galaxy's redshift tells us how much its light has been stretched. For very distant galaxies, that stretching is mostly dominated by the expansion of the universe. But in the local universe, extra motion can be a large part of the signal. A galaxy may be receding because space expands, while also falling toward a cluster, orbiting within a group, or being pulled sideways by a neighboring structure. Those motions mix together in the light we receive. So astronomers need independent distance methods. They look for certain kinds of variable stars. They use supernovae when they appear. They compare galaxy rotation with brightness. They study surface brightness fluctuations in older stellar systems. Each method has limits. Each method works best at certain distances. Each method has uncertainties that become important when the question is not simply how far away a galaxy is, but how it is moving through the cosmic web. This is why measuring the invisible force is not one measurement. It is a stack of measurements. Distance, redshift, sky position, galaxy type, cluster membership, dust correction, selection bias, velocity model, mass estimate. Every layer can sharpen or blur the final picture. If a galaxy is closer than we think, its extra motion is different. If a cluster is more massive than we think, its pull changes. If a hidden group lies behind the Milky Way's dust, an entire part of the gravitational map may be missing. If dark matter is distributed differently from the visible galaxies, the bright map does not fully match the real mass map. This is why the motion of the Milky Way is not a solved problem in the simple sense that a planet's orbit is solved. It is known well enough to reveal the main story, but complicated enough that the details still matter. And the details are not small. On human scales, a small error in a cosmic velocity model would be absurdly large. A difference of a few dozen kilometers per second is faster than any car, faster than most bullets, faster than the escape speed from some small worlds. In galactic dynamics, that same difference can be part of the uncertainty. The numbers are so large that the word precise has to be understood differently. Astronomy often asks us to accept a strange combination: enormous scales and delicate measurements. A tiny shift in a spectral line can reveal the motion of a galaxy. A slight microwave temperature difference can reveal the movement of our cosmic neighborhood. A faint X-ray glow can reveal hot gas inside a cluster hidden behind stars. A small statistical pattern across thousands of galaxies can point toward a gravitational basin hundreds of millions of light-years wide. The invisible force is not invisible because it leaves no trace. It leaves traces everywhere. It leaves them in redshifts. It leaves them in the CMB. It leaves them in the way galaxies fail to follow the expansion perfectly. It leaves them in the missing map behind the Milky Way. It leaves them in the fact that nearby galaxies seem to share directions of motion that cannot be explained by chance alone. But the traces are quiet. They do not look like a monster in the telescope. They look like numbers. They look like corrections. They look like arrows on a map. And behind those arrows is the motion of everything we know. Think about what that means for Earth. Every sunrise happens on a planet spinning through several kinds of motion at once. Every map on Earth is drawn on a surface that is rotating. Every human city is moving around the sun. Every orbit around the sun is being carried around the Milky Way. Every galactic orbit is inside a galaxy falling through a larger gravitational field. A person can sleep in a quiet room and still be part of a cosmic movement so large that its cause is measured in galaxy clusters. This does not make daily life less real. It makes daily life stranger. The stillness of a bedroom, a desert, an ocean, or a mountain is local stillness. It is not cosmic stillness. There may be no true stillness in the universe at all. Only motion measured against different things. The cosmic microwave background gives us one of the closest things to a universal reference. But even that is not a flaw. It is radiation from an early epoch, a background against which motion can be described. The universe does not come with a sign that says stationary. It gives us relationships, and our relationship to the ancient light says that we are moving. Once that is understood, the title of this story changes meaning. The invisible force pulling the Milky Way is not one hidden object waiting in the dark. It is the reason our galaxy has a velocity in the first place. It is the gravitational consequence of living inside a lumpy universe. If the cosmos were perfectly smooth, there would be no cosmic web to fall through. If there were no dark matter, galaxies and clusters would not have formed in the same way. If there were no tiny early density differences, the large-scale structure around us would not exist. If the Milky Way were truly alone, its path would be different. Our motion is therefore a clue that the universe has memory. Not memory like a mind, memory like a landscape shaped by its past. The early universe left tiny differences. Gravity preserved and amplified them. Those differences became structures. Those structures now guide galaxies. The Milky Way is moving because the universe remembers where matter gathered. That may be the most important idea in this first half. Motion is not random noise. It is a record. It is the present-day echo of ancient unevenness. When we trace the Milky Way's path, we are tracing the history of cosmic structure itself. For this video, the first half of the journey brings us to a clear picture. The Milky Way is moving. Its motion is measured against the cosmic microwave background and nearby galaxies. The cause is not one object, but a gravitational landscape. The Great Attractor is part of that landscape, associated with the Norma cluster and hidden partly behind the Milky Way's dusty plain. Larger structures, such as the Shapley concentration, may also contribute. Voids and dark matter help shape the flow, and our galaxy, with Earth inside it, is carried along without our bodies noticing anything at all. But the story is not finished. Because if gravity from dense regions can pull the Milky Way, then the opposite side of the map matters too. What lies behind us? What if part of our motion is not only attraction toward mass, but the result of a vast emptiness on the other side? What if the universe is guiding the Milky Way not just with the weight of galaxies ahead, but with the absence of galaxies behind? That idea changes the image completely. The galaxy is no longer simply falling towards something. It may also be moving away from a region where there is almost nothing to hold it back. And to understand that, we have to leave the Great Attractor for a while and look into the darker half of the cosmic map. The darker half begins with a word that sounds almost too simple: void. A void is not a wall. It is not a giant object hiding in the black. It is a region where there are fewer galaxies than average, fewer clusters, fewer bright knots of matter, and less gravity competing for control. From far away, that may not sound powerful. Emptiness seems passive. It seems like something that can only sit there and do nothing. But in the universe, even absence changes motion, because gravity is not only about what pulls strongly from one side, it is also about what does not pull from the other. Imagine standing in a wide field while people tug on ropes tied around you. If many people pull from one direction and almost no one pulls from the opposite side, you will move. You would describe the motion as being pulled forward, but the missing pull behind you matters just as much. Without it, there is no balance. That is the strange idea behind the cosmic repeller. The Milky Way may not be moving only because dense regions of galaxies are pulling it. It may also be moving because a large underdense region on the opposite side is not holding it back. To a galaxy inside the expanding universe, that missing gravity can look almost like a push. Not a push from a solid hand, not a pressure wave, not a hidden engine, a push made by imbalance. This is why the phrase can feel misleading at first. A void does not repel the Milky Way in the way a magnet repels another magnet. The void is not sending out a force. It is simply less massive than its surroundings. As space expands and matter falls toward denser regions, galaxies naturally move away from the emptier side, because the gravitational landscape is uneven. That is enough to change the path of entire galaxies. It is also enough to make the story of our motion more unsettling, because the thing guiding us may not be one monster in the distance. It may be a pattern spread across hundreds of millions of light years. On one side, dense superclusters pull. On the other side, vast underdense regions fail to pull back. The Milky Way sits between these differences and moves as part of the flow. This means our galaxy is not traveling through a neutral darkness. It is traveling through a landscape made of weight and absence. And both parts matter. And this is why the second half of the journey has to move slowly into that emptiness, because the missing galaxies are not background decoration. They are part of the reason the Milky Way has the path it has. To understand how astronomers even find something like this, we have to return to the problem of motion. If everything in the universe is expanding away from everything else on large scales, then a galaxy's motion is not as simple as pointing to a direction in space. There is the smooth expansion of the universe, and then there are local deviations from that expansion. Those deviations are called peculiar velocities. The name sounds small, almost harmless, but it is one of the most important tools in this story. A galaxy may be carried away by cosmic expansion, while also drifting toward a cluster, away from a void, or along a filament. To separate those motions, astronomers need distances, redshifts, and careful models of how space itself is stretching. Redshift tells us how much a galaxy's light has been stretched. Distance tells us where that galaxy actually is. Compare the two, and the difference can reveal whether the galaxy is moving a little faster or slower than the expansion alone would suggest. Do this for one galaxy, and you get a small clue. Do it for thousands, and a pattern begins to form. Galaxies do not drift randomly. Their motions bend toward dense regions, around walls, along filaments, and away from underdense space. The universe becomes less like a scattering of islands and more like a slow-motion weather map, where galaxies are the smoke particles revealing invisible currents. This is why cosmic flow maps look so strange and beautiful. They show streams of galaxies moving through enormous gravitational basins. They show where matter gathers, where paths converge, and where motion divides. The Milky Way is one point inside that map. A small point, but not an isolated one. When researchers map these flows, they find that our galaxy and its neighbors are part of a larger current. The local group, which includes the Milky Way and Andromeda, moves with many nearby galaxies. That motion is part of a regional pattern, not a private journey. The invisible force is therefore not just invisible because we cannot see the object causing it. It is invisible because it is distributed. It is written into the arrangement of matter around us. The pull is not one finger on the Milky Way. It is an uneven map of the universe, acting from every direction at once. This is where Laniakea becomes important again. Laniakea is often described as our home supercluster, but it is not a hard object like a planet, a star, or even a single galaxy cluster. It is better understood as a region of cosmic flow. Inside it, many galaxy motions tend to drain toward a common basin, like rainwater moving toward a low valley. That image is useful because it avoids a common mistake. A supercluster is not a thing with a sharp surface. There is no cosmic border patrol between Laniakea and the next structure. There is no glowing wall in space where one supercluster ends and another begins. Instead, astronomers trace velocity flows. They ask where galaxies would move after the expansion of the universe is removed from the picture. If the motions converge inward within a certain region, then that region can be described as a gravitational basin. The Milky Way is inside one of those basins. That alone changes the way we imagine our cosmic address. We do not only live in a solar system. We do not only live in a spiral galaxy. We do not only live in the local group. We live inside a moving river of galaxies. The terrifying part is that the river is larger than our senses can hold. On Earth, the ground feels still. The night sky looks quiet. The Milky Way appears as a soft band of light, as if it were fixed overhead. But in the deeper frame, the entire galaxy is part of a stream, shaped by structures so large that even light takes millions of years to cross them. A person can sleep through that motion. A civilization can build cities through that motion. The motion never becomes wind against our faces, because we move with the galaxy itself. Yet the motion is real. It is measurable. It leaves a mark in the cosmic microwave background. It appears in the velocities of nearby galaxies, and it tells us that the largest objects around us are not standing still either. They are flowing through the universe, pulled by the past. The cosmic microwave background gives the cleanest clue that we are moving. It surrounds the sky as ancient light from the early universe, stretched into microwaves after billions of years of expansion. In every direction, it is almost the same temperature. But almost is the key word. One side of the sky is slightly warmer. The opposite side is slightly cooler. Part of that difference is caused by our motion through the background. We are moving toward one side, so that ancient light is slightly blue-shifted. We are moving away from the opposite side, so it is slightly red-shifted. This dipole pattern works like a cosmic speedometer. It does not tell us that the Milky Way has an engine. It tells us that our local frame is not at rest compared with the early universe's afterglow. That is a profound idea. The oldest light we can observe becomes the reference frame for our motion now. The universe gives us a background, and against that background we discover that we are not motionless. Earth rotates. Earth orbits the Sun. The Sun orbits the center of the Milky Way. The Milky Way moves with the local group. The local group flows through larger structure. Layer after layer, stillness disappears. But the CMB dipole does not explain the cause by itself. It measures motion. To understand why the motion exists, astronomers have to map the nearby universe and ask what arrangement of matter could create it. That is where the story becomes messy, because the matter responsible is not neatly visible. Some of it is hidden behind the Milky Way. Some of it is spread through dark matter halos. Some of it belongs to clusters and superclusters. Some of it is the absence of matter in voids. And some of it may lie beyond the regions we have mapped well enough. This means the answer is not one sentence. It is a reconstruction, a cosmic investigation, a long attempt to understand why our part of the universe is drifting the way it is. The Great Attractor became famous because it seemed to offer a dramatic answer. Here was a region of space toward which many galaxies appeared to be moving. It sounded almost like science fiction, a hidden gravitational anomaly pulling the Milky Way across the cosmos. But the closer astronomers looked, the less simple it became. The Great Attractor region is not a single object. It is associated with massive galaxy concentrations, including the Norma cluster, and it lies in a direction partly blocked by the zone of avoidance. That zone is the strip of sky where the stars, dust, and gas of our own Milky Way make it difficult to see the universe beyond. So the very galaxy whose motion we are trying to explain also hides part of the answer. That is one of the most interesting details in the story. The Milky Way is both the subject and the obstruction. We are inside the thing we are trying to study. We look outward, through its dust. We infer what lies behind it, with radio observations, infrared surveys, X-rays, redshift measurements, and mathematical reconstructions. The map improves, but it never arrives all at once. For a long time, the Great Attractor sounded like the final answer. Then, Shapley became important. The Shapley concentration is much farther away, a huge concentration of galaxy clusters beyond the Great Attractor region. It is one of the densest known structures in the nearby universe. Its gravity may contribute to the motion of our region as well, especially when astronomers look at the larger scale flow. That is the pattern again. A simple explanation becomes a layered one. The Milky Way is not only pulled by one nearby overdensity, it may be affected by a chain of mass concentrations stretching across vast distances. The Great Attractor matters. Shapley may matter. Laniakea matters as a flow basin. Voids matter because they create imbalance. Dark matter matters because it supplies most of the gravitational structure. And cosmic expansion matters because it sets the background on which all these motions ride. This is why the invisible force is terrifying in a quiet way. It is not terrifying because it is about to destroy us. It is terrifying because it reveals how deeply we are embedded in systems we cannot feel. The entire Milky Way can be steered by structures our ancestors could not even imagine. No sound, no warning, no visible engine. Just gravity, emptiness, and time. The idea of a repeller adds another layer. When scientists speak about the dipole repeller, they are describing a region that appears to influence local motion from the opposite direction of the main attractors. In ordinary language, it sounds as if an enormous void is pushing galaxies away. But the physics is more subtle. In an expanding universe, underdense regions expand faster relative to denser regions because there is less matter to slow them down. Around a void, galaxies tend to move away from the underdense interior and towards surrounding denser structures. From the viewpoint of a galaxy outside the void, that can resemble a repulsive effect. Again, nothing is firing a beam, nothing is blowing a wind. The void is simply less gravitationally attractive. That absence creates motion. This is a difficult idea because human intuition is built for solid things. We understand a planet pulling on a moon. We understand a hand pushing a door. We understand water flowing downhill. But a galaxy drifting away from emptiness is stranger. It asks us to think of space not as a blank stage, but as a gravitational landscape where even missing mass shapes the route. The cosmic map then begins to look like terrain. Dense clusters are valleys, voids are highlands. Galaxies move along slopes, not because there are roads, but because gravity defines the slopes. This is not a perfect comparison, but it helps. If the Milky Way is falling through the terrain, then the force pulling it is not located at a single destination. It is the shape of the land itself. That shape was seeded long before galaxies existed. In the early universe, matter was almost evenly distributed, but not perfectly. Tiny density differences existed. Some regions had a little more matter than average. Others had a little less. Gravity slowly amplified the richer regions. Expansion stretched the whole scene. Dark matter gathered first. Ordinary matter followed. Gas cooled. Stars formed. Galaxies assembled. Clusters grew, and empty regions became emptier by comparison. Over billions of years, the small differences became cosmic architecture. The Milky Way is now moving through that architecture. So when we ask what is pulling our galaxy, we are also asking what the early universe looked like in microscopic detail. The answer is ancient, older than the Milky Way, older than the Sun, older than every planet. The motion we measure today is a fossil of the universe's first unevenness, preserved on a scale too large for ordinary life to notice. That makes the topic feel less like astronomy and more like cosmic archaeology. We are not only tracking where our galaxy is going, we are reading a message left by the early universe in the motion of galaxies. But the message is incomplete because the map is incomplete. A galaxy survey is only as good as the distances it measures, the sky it covers, and the methods used to see through dust. The zone of avoidance still matters because our own galactic disk blocks optical views in certain directions. Instruments have improved, but some structures remain harder to chart than others. Infrared observations can peer through dust better than visible light. Radio surveys can detect hydrogen in galaxies hidden from optical view. X-ray observations can reveal hot gas in galaxy clusters. Each method adds a different layer. None of them alone gives the entire answer. This is why the Great Attractor mystery did not disappear after one discovery. It evolved. The question shifted from, what is the one thing pulling us, to, what combination of structures explains the motion we observe? That shift is important for the script of the universe itself. The first version is dramatic, but too simple. The second version is quieter, but far more real. Our galaxy is not being dragged by one hidden monster. It is responding to a large-scale pattern that includes attractors, repellers, filaments, walls, voids, and dark matter. That pattern is not static. Clusters grow, galaxies merge, voids expand. The universe itself continues to stretch. The map is alive in slow motion, not alive biologically. Alive as a changing structure. Every few 100 million years, galaxies shift enough for the picture to be different. The Milky Way and Andromeda draw closer. Dwarf galaxies are captured or disrupted. Star formation changes. Superclusters continue their partial motions, while cosmic expansion pulls distant structures away. On the larger scales, the universe does not behave like a machine rotating around a center. It behaves like a web whose knots, threads, and open spaces evolve together. This is the scale where the word direction becomes strange. On Earth, a direction feels local. North, south, east, west, up, down. For the Milky Way, direction means a path through the cosmic web, toward denser regions away from emptier regions, along flows that extend far beyond the galaxy's own disk. The galaxy's spiral arms, its central bar, its stars, planets, dust lanes, and dark halo all move together through that wider pattern. The Sun does not choose the path. Earth does not choose it. Life does not choose it. We are passengers inside a moving galaxy, and the driver is the distribution of matter in the universe. This is where the title becomes literal. The invisible force pulling the Milky Way through space is gravity, but not gravity from one neat source. It is gravity as geography. It is gravity made from superclusters, voids, and dark matter. It is the result of a cosmic landscape too large to see from inside a single galaxy. The reason we call it invisible is not that there is nothing there. It is that most of the cores cannot be held in one image. You can show the Norma cluster. You can show a map of Shapley. You can show the cosmic microwave background. You can show the Milky Way hidden behind its dusty plain. You can show galaxies streaming through Laniakea. But you cannot point to a single glowing object and say, there, that is the whole answer. The whole answer is the imbalance. That is less simple, but it is more terrifying, because it means the universe controls motion through structure, not through obvious signs. There may be no visible marker in the night sky showing where the Milky Way is headed. No arrow, no bright destination, no cosmic lighthouse. Only the measured drift of galaxies and the background glow of the early universe. Even the idea of being pulled through space can be deceptive. The Milky Way is not moving through an empty container like a ship crossing an ocean. Space itself is expanding. Galaxies have local motions within that expansion, and those motions are shaped by gravity. The galaxy's path is therefore not a line drawn across a fixed room. It is a motion within a changing space-time. This matters because it prevents another common misunderstanding. The universe does not have a center that all galaxies orbit. The Great Attractor is not the center of the universe. Shapley is not the center of the universe. Laniakea is not a cosmic capital city. They are local and regional features in a universe much larger than the maps we usually discuss. Our motion is important to us because we live inside it, but the universe contains countless other flows, basins and structures. Other galaxies have their own local motions. Other clusters are shaped by different nearby masses. On the largest scales, these patterns average into the cosmic expansion, but locally, they create complexity. That complexity is why astronomy often feels like humility disguised as measurement. We measure a number and discover a motion. We map a cluster and discover a larger web. We name an attractor and discover a repeller. We define a supercluster and discover that its boundaries are more like flow lines than walls. Every answer makes the universe less simple, but not less understandable. That distinction is important. The story is not that everything is mysterious and therefore unknowable. The story is that the universe is difficult in a way that rewards better maps. The more carefully astronomers measure, the more the motion begins to make sense. The cosmic microwave background tells us how fast we move relative to the early light. Galaxy surveys show where matter is concentrated. Peculiar velocities reveal the flows. Dark matter models explain why visible galaxies alone are not enough. Large-scale simulations test whether the structures we observe can create the motions we measure. Each piece reduces the mystery, but never turns it into a simple object. That is why the invisible force remains fascinating. It becomes clearer without becoming ordinary. If you could somehow step far outside the local group and watch the region around us in accelerated time, you would not see the Milky Way flying like a bullet through empty space. You would see a slow gravitational choreography. Clusters would draw matter inward, voids would grow emptier, filaments would guide galaxies. The Milky Way and Andromeda would move toward each other. Nearby dwarf galaxies would orbit, fall in, or be torn apart. The whole local group would drift within the larger flow. Scale it up further, and the scene would become even stranger. Galaxy concentrations would look like glowing threads and knots. Voids would appear as huge dark bubbles. Motion would not be random. It would follow the web. The Milky Way's path would be one small curve among many. That image may be more accurate than the idea of a single pull. Our galaxy is not the main character of the universe. It is a particle in a vast flow, a luminous island carried by an invisible current. That current is made from gravity, but gravity here is not intimate like the gravity that keeps your feet on the ground. It is slow, patient, and enormous. It does not need to hurry. It has billions of years. It does not need to announce itself. It works through every star and every particle of dark matter, through every cluster ahead and every void behind. This is why nothing about daily life reveals it. A tree does not lean because the Milky Way is moving. The oceans do not slosh to one side. Your body does not feel the galaxy's drift. Inside the galaxy, everything nearby shares the motion. The only way to notice it is to look beyond the galaxy, compare ourselves with the ancient background, and measure the large-scale structure around us. That is a powerful thought. The most important motions in our cosmic life are invisible until we build instruments that can compare us with the universe itself. A compass cannot show them. A telescope alone cannot fully explain them. A single photograph cannot capture them. They emerge from maps, measurements, and time. That makes the topic perfect for a calm space journey, because the fear is not loud. It is not an asteroid impact. It is not a nearby supernova. It is the quiet realization that our entire galaxy has a trajectory, and that trajectory was written by structures beyond human scale. But to understand the ending of that trajectory, we have to ask what happens next. Where is the Milky Way actually going? The honest answer is not a single destination. On a local scale, the Milky Way and Andromeda are moving toward each other. In several billion years, they are expected to merge into a larger galaxy, or at least pass through a long gravitational interaction that reshapes both systems. That future is not caused by the Great Attractor. It is caused by the mutual gravity of the local group. On a larger scale, our region moves within the flow of Laniakea and toward the general direction associated with major mass concentrations. On an even larger scale, cosmic expansion changes the long-term relationship between distant structures. These layers do not cancel each other. They stack. The Moon orbits Earth. Earth travels around the Sun. The Sun orbits the Milky Way. The Milky Way approaches Andromeda. The local group participates in larger cosmic flows. The universe expands around all of it. When people ask where we are going, they often want one answer, but the universe gives several, depending on scale. This is not a flaw. It is the only way motion works in a universe with structure. For the Sun, the Milky Way is the mainframe. For the Milky Way, the local group matters. For the local group, surrounding superclusters and voids matter. For the largest visible universe, expansion dominates. Every motion is real inside its frame. That is why the Milky Way can be moving toward Andromeda and also participating in a broader flow through space. It is why Earth can feel still while racing around the Sun. It is why human intuition struggles with cosmic motion. We want one speed and one direction. The universe gives nested motion. Now imagine the future after the Milky Way and Andromeda merge. The local group becomes more bound to itself. Distant galaxies outside our gravitational neighborhood continue to recede as the universe expands. Over immense timescales, many galaxies beyond the local group may become unreachable and eventually unobservable, depending on distance and cosmic acceleration. This gives the invisible force a tragic edge. Today, we can map large structures because their light still reaches us. We can compare our motion to the cosmic microwave background. We can observe superclusters, voids, and flows. But in the deep future, the sky may offer less information. Distant galaxies may fade beyond horizons. Future observers, if they exist, may see a quieter universe and have fewer clues about the large-scale flow that shaped their history. We live at a time when the cosmic map is still visible enough to study. That is not guaranteed forever. The invisible force pulling the Milky Way is therefore not only a present-day question, it is also a question about timing. We are here while the evidence can still be collected. We are here while the ancient background is still detectable. We are here while galaxy surveys can still reveal walls, filaments, clusters and voids across hundreds of millions of light years. That makes our era unusually fortunate. Not safe, not central, but fortunate. We can see enough of the cosmic web to understand that we are part of it. The story also changes how we think about darkness. Between the bright galaxies in a map, the dark spaces may look like nothing. But those spaces help define the motion. A void is not simply an empty backdrop. It is a structural feature. Its lack of mass affects how surrounding matter moves. In that sense, the universe is shaped by both presence and absence. Stars make light, galaxies make islands, clusters make knots, dark matter makes hidden scaffolding. Voids make open regions where gravity is weaker. Together, they create motion. That is one of the most elegant ideas in cosmology. The Milky Way is not pulled by light alone. It is guided by a map where darkness has weight. Not because darkness is matter, but because the lack of matter changes the balance. This is why a void can be as important as a cluster. A cluster says, "Come this way." A void says, "There is less here to hold you." Between those two facts, galaxies flow. The terrifying part is how calmly it happens. No galaxy decides. No star resists. No planet negotiates. Gravity does not care whether a civilization notices. For billions of years, the Milky Way has followed these larger patterns while life emerged on one small planet inside it. Single-celled organisms appeared, oceans changed, continents moved, dinosaurs lived and vanished, mammals spread, humans looked up, telescopes were built, satellites were launched. And only then did we begin to understand that even our galaxy has a motion through the larger universe. The motion was always there. The knowledge was new. That difference is humbling. The universe does not become bigger when we learn about it. Our awareness does. And awareness can be frightening because it removes the illusion of stillness. Before modern astronomy, the night sky could seem like a fixed dome. Then Earth moved. Then the Sun moved. Then the Milky Way became one galaxy among many. Then galaxies were found to be moving away with the expansion of space. Then local motions revealed that galaxies also drift through the cosmic web. Every step moved us farther from the center of the story. But every step also gave us a better story. The Milky Way is not a fixed home floating in a quiet universe. It is a moving structure inside a living map of gravity. If that sounds unsettling, it should. But it is also beautiful, because it connects our galaxy to the rest of the cosmos in a physical way. The same gravity that shapes planetary orbits also guides galaxy flows. The same early density variations that helped form the first structures still influence motion now. The same dark matter that holds galaxies together also helps build the larger web around them. Everything is linked by scale. A planet orbits because of gravity. A star moves through a galaxy because of gravity. A galaxy flows through a supercluster because of gravity. The law is familiar. The scale is not. That is where wonder enters. The invisible force is not magic. It is ordinary physics applied to an extraordinary amount of matter and time. It is terrifying because the ordinary becomes alien when stretched across the universe. A falling apple is familiar. A falling galaxy is not. yet both belong to the same deep pattern. At this point, the question becomes less about whether something is pulling the Milky Way and more about what kind of universe makes such pulling possible. The answer is a universe with structure, not a perfectly smooth universe, not a random scatter, a universe with filaments, clusters, voids, dark matter halos, and ancient density differences amplified by gravity. If the early universe had been perfectly smooth, there would be no galaxies, no stars, no planets, no Milky Way to pull, no Earth to ask the question. The same unevenness that makes our galaxy move also made our existence possible. This is one of the strangest turns in the story. The force that removes our sense of cosmic stillness is part of the same history that created a place for life. A perfectly balanced universe might have been peaceful, but empty. A slightly uneven universe became dangerous, structured, luminous, and alive. The Milky Way's motion is therefore not a mistake in the map. It is evidence that the universe is the kind of place where structure can grow. And structure is why there are stars. Without gravitational imbalance, there is no story. This does not make the motion less frightening. It makes it more meaningful. The galaxy is moving because the universe was never perfectly equal in every direction. Those tiny differences became everything. Now, long after the first light, our galaxy still responds to them. That response is written across the sky in ways we have only recently learned to read. When astronomers build maps of cosmic flows, they are not just drawing where galaxies are. They are drawing where gravity has been working for billions of years. Each velocity arrow is a piece of history. Each cluster is a concentration of long-term collapse. Each void is a region where matter thinned and expansion won more easily. The map is not only spatial, it is temporal. It shows what the universe has been doing. This is why the subject can hold a long documentary without becoming empty, as long as the script keeps moving from clue to clue. The CMB gives one clue, galaxy redshifts give another. The zone of avoidance creates a problem. Infrared and radio surveys help solve part of it. The Great Attractor gives one layer. Shapley adds another. Laniakea reframes the region as a flow basin. The dipole repeller reminds us that absence matters. Dark matter adds hidden mass. Cosmic expansion adds the background. Future acceleration adds a final horizon. The story is not one repeated sentence. It is a chain of evidence. And the chain leads to a view of the Milky Way that is very different from the one we feel from the ground. From Earth, the galaxy is our home. From the cosmic web, the galaxy is moving matter. From the CMB, it is a frame with a velocity. From future cosmology, it is one temporary island in a universe, becoming more isolated over time. Each frame is true. None is complete alone. This is why no final image can fully capture the invisible force. A dramatic thumbnail might show the Milky Way being pulled by a glowing hand or dragged toward a dark mass. But the real answer is more subtle. The force is not an object. It is the combined result of the matter distribution around us. If we wanted to visualize it honestly, we would show a web. Galaxies as lights, clusters as bright knots, voids as enormous dark cavities, flow lines curving through the map. The Milky Way as a tiny point on one stream, the Great Attractor ahead, in one layer, Shapley farther beyond, an under-dense region behind, dark matter invisible around all of it. That is the real picture. It is less simple than a monster in space, but more powerful because it is real. The galaxy is being guided by the architecture of the universe, and we are inside the galaxy, unable to feel the motion, but able to calculate it. There is something almost strange about that contrast. Our bodies are blind to the motion. Our mathematics is not. Our senses say stillness. The universe says velocity. This is what science often does. It does not merely show us new things. It corrects the scale of our instincts. It teaches us that familiar feelings are not always accurate guides to reality. The ground feels flat. Earth is round. The sun looks like it crosses our sky. Our planet turns beneath the sky. The stars look fixed. They move. The Milky Way looks like home. It is home, but it is also falling through a gravitational landscape. The correction does not destroy the beauty. It deepens it. Because now, the night sky is not only a ceiling of stars, it is a moving reference frame inside a larger flow. When you look toward the Milky Way on a dark night, you are looking into a galaxy that is rotating, merging, drifting, and responding to structures beyond ordinary imagination. Every star in that band shares the broad fate of the galaxy. Every planet inside it is along for the ride. The invisible force does not need to announce itself, because it is already included in the motion of everything around us. That is why the ending of this story should not pretend there is one final answer hiding in one place. The better ending is this: the Milky Way is being pulled, but not by a single secret object. It is being carried through a cosmic flow created by dense regions, empty voids, dark matter, and the ancient unevenness of the universe itself. The Great Attractor is part of the story. The Shapley concentration may be part of the story. Laniakea gives the motion a larger basin. A repeller-like underdensity may help explain the opposite side of the flow. And the cosmic microwave background gives us the quiet evidence that our local frame is not still. All of these pieces are needed. Remove one, and the picture becomes too simple. Add them together, and the terrifying force becomes visible in a new way. Not as a glowing object, not as a monster, not as a hole in space, as a map. A map so large that our galaxy is only a moving point inside it. That may be the deepest fear in the topic. Not that something is pulling us toward immediate disaster, but that our entire home galaxy is part of a motion written on scales so large that human life feels almost motionless by comparison. We build houses, we measure years, we watch seasons change. Meanwhile, the Milky Way moves through the universe at hundreds of kilometers per second, guided by structures whose light crossed space before human beings existed. The galaxy does not ask whether we understand. It moves anyway. And somewhere beyond the stars we can see with our eyes, beyond the dust that hides part of the map, beyond the clusters whose gravity bends the flow, beyond the voids whose emptiness changes the balance, the largest pattern around us continues to shape our path. Quietly, patiently, invisibly. There is another practical reason the answer remains layered. Distance itself is difficult to measure. In ordinary life, distance can be checked with a ruler, a map, or a signal. In cosmology, distance becomes a ladder. Nearby stars can be measured with parallax, the tiny shift in their position as Earth moves around the Sun. More distant objects require other methods: variable stars, standard candles, galaxy relations, supernovae, and redshift-based estimates. Each step depends on the one before it. That means a cosmic flow map is not only a picture, it is a construction built from many kinds of measurement. If a galaxy's distance is slightly wrong, its peculiar velocity can look slightly wrong. If many distances are uncertain, the flow becomes blurry. If dust hides a region, the map develops a blind spot. If dark matter dominates a structure, visible galaxies may only trace part of the true gravitational field. This is why the invisible force cannot be reduced to one dramatic arrow. Even the arrow has to be earned. Astronomers need to measure where galaxies are, how fast they appear to recede, how much of that recession belongs to cosmic expansion, and how much remains as local motion. Then, they need to compare thousands of such measurements and ask what gravitational landscape could create the pattern. This is slow work. It is not one telescope looking at one object. It is decades of sky surveys, catalogs, instruments, corrections, and models. The result is a universe that becomes visible not only through light, but through motion. A cluster can reveal itself by the galaxies inside it. A void can reveal itself by what is missing. A dark matter concentration can reveal itself by gravitational effects. A flow can reveal itself by the way galaxies refuse to follow smooth expansion exactly. In that sense, the Milky Way's motion is not just a fact about our galaxy. It is a tool. It helps probe the mass around us. It helps test whether our map of nearby structure is complete enough. It helps reveal which regions are pulling, which regions are underdense, and which structures belong to the same gravitational story. This turns the Milky Way into a kind of cosmic test particle. Not deliberately, not uniquely, but physically. Its motion tells us something about the field it moves through. Just as a leaf carried by a river reveals the direction of the water, a galaxy carried by cosmic flow reveals the shape of the gravitational current. But unlike a leaf, the Milky Way is massive, structured, and full of its own internal motions. Stars orbit inside it. Gas clouds move through spiral arms. Satellite galaxies circle around it. Dark matter surrounds it in a vast halo. The galaxy is not a rigid stone sliding through space. It is a living gravitational system moving inside an even larger one. This is another reason the topic is so large. There is motion inside motion. The Sun circles the galactic center, while the galaxy as a whole moves through the local group. The local group moves in relation to nearby clusters. Nearby clusters flow toward larger concentrations. All of it is carried within the expansion of space. A simple animation might show one clean path. Reality is nested. The Sun's orbit around the Milky Way does not stop because the Milky Way is drifting. Earth's orbit around the Sun does not stop because the Sun is orbiting the galaxy. The Moon's orbit around Earth does not stop because Earth is moving through the solar system. Each smaller motion rides inside a larger frame. This is why there is no contradiction in saying we are both circling and traveling. We are doing both. The galaxy is doing many things at once. The hard part is choosing the frame that answers the question being asked. If the question is why the stars in the Milky Way orbit the center, the answer lies in the galaxy's mass distribution, including dark matter. If the question is why the Milky Way and Andromeda approach each other, the answer lies in their mutual gravity inside the local group. If the question is why the local group moves relative to the cosmic microwave background, the answer lies in the larger distribution of matter and emptiness around us. The title points to that last layer, the biggest motion, the one we cannot feel, the one that turns our entire galaxy into a passenger. To make this even stranger, some of the most important matter involved is not luminous at all. Dark matter does not shine, reflect, or absorb light in the normal way. We infer it because galaxies rotate too quickly for visible matter alone. Clusters hold together with more gravity than their stars and gas can provide. Gravitational lensing bends light as if unseen mass is present, and the large-scale structure of the universe forms in ways that require more than ordinary matter. So when we say superclusters pull on the Milky Way, we should not imagine only the galaxies we can photograph. Each visible cluster sits inside a larger dark matter structure. Each galaxy is surrounded by a halo. Each filament may trace invisible scaffolding. The light is the decoration. The gravity comes mostly from what we cannot see directly. This makes the invisible force doubly invisible. First, because the total cause is spread across space. Second, because much of the mass shaping it is dark. A map of bright galaxies is only a partial map of gravity. It is like seeing city lights from orbit and trying to infer the roads, mountains, rivers, and borders below. The lights help, but they do not show everything. Cosmological simulations help fill the gap. Scientists begin with tiny density fluctuations like those seen in the cosmic microwave background. They add dark matter, ordinary matter, expansion, gravity, and time. Then they watch structure grow inside a computer universe. If the simulated universe produces webs, clusters, voids, and flows similar to the real ones, the model gains strength. This does not mean the simulations are perfect copies. It means they test whether the underlying physics can build the kind of universe we observe. They show how small early differences become massive late structures. They show how voids expand. They show how filaments gather matter. They show how clusters become gravitational basins. They show why galaxies do not simply sit in place. In that way, the Milky Way's motion becomes part of a much larger conformation. Our galaxy is doing what galaxies should do in a universe like ours. It moves because it formed inside an uneven cosmos where gravity has had billions of years to work. That explanation is satisfying scientifically, but emotionally it can feel colder, because it means there is no special protection around our home. The Milky Way is subject to the same cosmic rules as every other galaxy. It can be pulled, it can merge, it can be reshaped, it can lose stars, it can absorb smaller galaxies. It can drift inside flows no living thing can feel. A galaxy with life inside it is still a galaxy. The universe does not treat it differently. This may be the quietest, terrifying idea in the whole video. Not that the motion is dangerous tomorrow, not that the Great Attractor will swallow Earth, not that some hidden object is waiting to destroy the Milky Way, but that the existence of life does not remove the galaxy from cosmic mechanics. We are precious to ourselves. To gravity, we are passengers. The Milky Way's path is decided by mass, distance, time, and expansion. Human history does not change it. Our wars, cities, languages, machines, and dreams all happen inside a galaxy whose motion began long before us and will continue long after us. That does not make human life meaningless. It makes the stage enormous. It means everything we do happens while the galaxy moves through a universe whose largest structures were born from conditions near the beginning of time. Even the future collision with Andromeda belongs to this same theme. From Earth, if life or its descendants were somehow still around when the night sky began to change, the view would be spectacular. Andromeda would grow larger over millions of years. Its stars would fill more of the sky. The two galaxies would interact, stretch, distort, and eventually settle into a new shape. But even that dramatic merger would not remove the local group from the larger story. A merged Milky Way Andromeda galaxy would still exist inside an expanding universe. It would still have a history of cosmic flows. It would still be part of a region shaped by earlier structure. The details would change, but the principle would remain. Gravity builds islands, then larger islands, then networks of islands. Expansion stretches the distances between networks. Voids grow. Bound systems remain together. Unbound systems drift apart. In the very deep future, the balance between gravity and expansion becomes one of the main facts of the cosmos. Structures that are gravitationally bound can stay together. Structures beyond that connection can recede ever farther. This is why the local future and the cosmic future can feel so different. Locally, the Milky Way and Andromeda may merge. Cosmically, the most distant galaxies continue to disappear beyond reach. So the invisible force pulling us now does not guarantee an endless journey toward all the matter we can see. Some flows are local, some structures are bound, others are not. The universe is not one single object collapsing together. It is a vast expanding space-time where gravity wins in some regions and expansion wins across the largest distances. That tension makes the story more precise. The Milky Way is not being pulled toward the center of everything. It is moving within a regional gravitational field. There is no center of everything. There are only structures, flows, and horizons. That is a crucial distinction, because the words Great Attractor can make people imagine a cosmic drain, as if all galaxies are sliding toward one final hole. But that is not what the evidence shows. The Great Attractor is a regional feature. The Shapley concentration is another large feature. Voids influence local flows. Laniakea is a flow-defined supercluster. None of these is the universal destination. The universe is too large and too dynamic for that simple picture. This is why the best explanation is also the least cinematic. The Milky Way is not doomed by one object. It is participating in the cosmic web. And the cosmic web is the real giant. The web is not a solid thing. It has no surface. It is made from the distribution of matter, galaxies, gas, dark matter, clusters, filaments, sheets, and voids. The Milky Way is one bright point in one part of that web, and its motion makes sense only when the web is considered. Once that image settles in, the question changes one last time. Instead of asking what is pulling the Milky Way, we can ask why the universe has a web at all. The answer goes back to the earliest measurable pattern in the cosmos. The cosmic microwave background is nearly uniform, but its tiny temperature differences reflect tiny density differences in the early universe. Those differences are the seeds of structure. Gravity amplified them. Dark matter helped them grow. Ordinary matter fell into the wells. Stars and galaxies lit up inside them. The web is the mature form of those seeds. The Milky Way's motion is one of the web's consequences. This means the invisible force is not a separate mystery placed on top of cosmology. It is cosmology in motion. It is the early universe still shaping the present. That makes the topic feel less like a single phenomenon and more like an entire lesson hidden inside. One question: why is the Milky Way moving? Because the universe has structure. Why does the universe have structure? Because the early universe was not perfectly smooth. Why do structures pull and guide galaxies? Because gravity acts on mass and responds to imbalance. Why do voids matter? Because missing mass changes the gravitational field. Why can we detect the motion? Because the cosmic microwave background gives us a reference frame, and galaxy surveys reveal local flows. Each answer opens another layer. That is the right kind of depth for a long space documentary. Not repetition, layering. A viewer should feel that every few minutes the camera moves to a new scale. Earth, Sun, Milky Way, Local Group, Great Attractor, Shapley-Laniakea, Dipole Repeller, Cosmic Web, Early Universe, Far Future. The story stays calm, but it does not stand still. That is also how the universe itself behaves. Calm on human timescales, restless on cosmic ones. From a human lifetime, the Milky Way's path is unchanging. No one will watch our galaxy noticeably shift against the cosmic web. The motion is too vast and too slow compared with our lives. But from the perspective of hundreds of millions or billions of years, galaxies move, merge, fall, and flow. The calmness is a trick of scale. The terror is realizing the trick. We are used to danger being fast. Fire, impact, storm, collapse. Cosmic motion is different. It can be enormous without being sudden. It can be unstoppable without being violent. It can shape the fate of galaxies while remaining invisible to every creature living inside them. That is why the title works. The invisible force is not scary because it attacks. It is scary because it is bigger than attack. It is the background condition of our cosmic life. It has been here the entire time. It will remain long after the video ends. And everything we know is moving with it. The force pulling the Milky Way through space is not one thing waiting in the dark. It is the dark and the light together. The crowded regions, and the empty ones. The matter we see and the matter we infer. The ancient ripples and the modern flow. The entire uneven universe still reaching into the present through gravity. And that is what makes it terrifying. Not because it will suddenly tear the galaxy apart, but because it proves that even the Milky Way, with hundreds of billions of stars, is not free from the larger shape of the cosmos. It is moving inside it, and so are we.